Hello, everyone. This week, we will talk about energy transition. This is a emerging and very interdisciplinary, comprehensive topic that by no means we will discuss this in the depth needed to address all aspects in energy transition. We will try to capture the main message, at the same time offer a few case studies to show what really drives energy transition and what we need to consider when we think about different countries and how to achieve carbon neutrality through energy transition in those contexts. Some sample analytical questions as usual. We will discuss what are the drivers of energy transition. We already know it's very important for us to transit to a lower carbon energy systems or net zero carbon emission energy systems. And how should each country think, design, or implement its energy transition? Each country has its own resources endowment, its own infrastructure, and its own economic budget, and those or even its own regulatory and policy considerations. Those are all very important and will have to be considered when we think or design or implement energy transition strategies. How to frame the role of different technologies in energy transition. We discussed levelized cost of electricity to try to compare different technologies. But at the same time, different technologies have different applications or social political acceptability, or the technology might impact by some of the factors as we will discuss in the next question, how geopolitics, wars, and pandemic, for example, impact the energy in transition. Those are some of the emergent trends or factors that will have large impact how we think about our energy transition. Some might serve as an accelerator, some might create impede the process. Those are the uncertainties. So first, let's look at the long history of human energy use. This chart shows the total energy consumption in the United States from when the country was created to 2017, and you can see first mostly use biomass, then coal is catching up, and that drives the industrial revolution, and then petroleum or oil exceed coal so as primary energy, and that's mostly driven by the wider use of automobile, the transport use of energy. And natural gas play a big role, and you can observe that starting from about 2000, and due to the implications or technology advancement in the shale gas revolution and the use of natural gas exceed coal, and that present a really fascinating story about how technology change impact our energy use. Nuclear as serving first increased very fast, then plateaued, due to the fact that it's very hard to for the public to accept to build new nuclear power plants. And since about 2000, and renewables are really taking off, and its speed it's really fast, given renewables in many countries or in many parts of the world have achieved grid parity. One milestone in the US is in 2019. For the first time, the energy US consumed from renewables exceed those from coal. So that's a major milestone that US use more energy from renewables than coal, and this trend is still happening. As I mentioned, it's partially due to the fact that more power plants are using natural gas as fuel. At the same time, they are growing renewables. So both forces drive the decline of coal, and that trend has continued. In the US, though, in other countries, we will discuss more later, but this is a encouraging news, and is still ongoing. So those different factors, as I mentioned, in the US context, demand was 24% less than projected. This is for 2020, and compared to the projections in 2005 by US Energy Information Administration. And renewables is about 79% more than projected, and I mentioned that's due to the fact of declining renewable cost, and renewables really expanding very fast. Nuclear provide about 20% of the total generation and has been plateaued. And natural gas expand doubled more than in 2005, benefit from the shale gas revolution. So those replace the use of coal and oil, which is about 70% less than projected. That all combined contribute to about 50% lower than the projected carbon emission. So that's really offers some optimism that if we combine all the efforts from energy efficiency, renewable expansion, and continue using of nuclear and the bridge fuels such as natural gas, and we can replace fossil fuel relative fast, or much faster than we had expected. And this is really what's has been happening. If this offers some optimism that US power sector is halfway to achieve 100% of decarbonization. That's compared to the projected, though. If we compare to 2005 real, that's about 25 to 30% of a reduction. If we look back in the history, one major figure that really shaped the source of the US energy strategy is Mr. Emery Lovins, who is an energy strategist and energy thinker, and now the chairman of Rock Mountain Institute, a major think tank in the energy policy field. And back in 1976, he published a very thoughtful, impactful piece on energy strategy, discussing the future energy systems the US might have. And he described there are two different paths that the US can take. One is soft path, one is hard path. The hard paths are dominated by central, larger scale, increasing supply and demand technologies such as fossil plants, nuclear will provide most of the energy need, and that is a hard path, or in today's term, more business as usual. That's one scenario. While in another scenario that US will use more flexible, resilient, sustainable, and benign energy sources, such as more use of renewable energy, have more energy efficiency measures, and try to match in scale and quality to the end use need of what technology we take, more distributed, more microgrid, for example. So in this scenario or soft path, it creates more resilient energy systems while satisfying the energy need. So this paper was published in 1976, and you can think about what insights it offers. And today, the energy use in the United States is about 100 quads, which is here. So it's more in towards to a soft path, but not fully. And that's the both good news and bad news that we are doing something, but not as much as Emery Lawrence had envisioned. So that offers a future path but the discussion of a soft path versus hard path really offers some strategic and insightful observation that help the policymakers, the policy debate, and the research to see what path really hope to adapt. Both paths, have totally different. Those two paths have totally different vision and different impacts on the costs, environmental impacts, human health impact, maybe water impacts too. So it's something that we hope our class can really push you to think more. And this really set up a good example for how to frame the questions or the challenges. So let's discuss what are the drivers of energy transition. For sure, we already discussed the growing demand. How can we satisfy the growing demand from more renewable, resilient, yet affordable and reliable sources? That's from the supply side. Those are all challenges. That's where there is a challenge, there is a driver for change. We also discussed the challenge of climate change. We have to reduce our carbon emission. and we need use more from lower carbon energy sources. Environmental pollution, we discussed the environmental impacts of our energy systems, and using examples from India and China, that how air pollution really create a concern of the public and drive the policy change and a series of change on what technologies and what policy measures to really drive energy transition, so to reduce the air pollution. And also energy security. This is especially during the context of the Ukraine crisis, that European countries face the supply of energy, and to secure its supply. And there are impacts of energy security, impacts of spiking energy price, and how different population groups will be impacted by those high prices. And some disadvantaged groups may just cannot afford it, their energy during cold winter. Also about economics, I mentioned renewables costs really coming down, and that's a fundamental driver for the expansion of renewables. So in the energy transition research, there are a very interesting case to talk about what the pathway should be. There are advocacy of 100% of renewables. Renewables in this context means solar, wind, and hydro, or solar, wind, water resources. And one of the flagship or represented researcher, Professor Mark Jacobson in Stanford University, which has now publishing in 100% of renewables for all purposes, and try to present a attractive or visionary case that from resources, technology, economic-wide, 100% renewables is not just possible, but also technical viable and economic cost effective, while creating huge benefits of pollution reduction, carbon mitigation, and economic benefits. So that's one school of researchers that want to have 100% of renewables, while other school discussions is 100% renewables really viable or even necessary. Those try to argue that the 100% of renewables has modeling errors, has implausible assumptions, or the representation of the model is not sufficient, and it needs better modeling in order to make the results more convincing. Because renewables has its challenging, it's variable, and it would need storage or long-term, especially long-term storage, and it also involves transmission lines, and how to operate the grid, and how to prepare the reserve. You have to think about more techniques of how to operate the grid, rather than just think about it's technically possible to have 100% of renewables. There are multiple challenges in order to make 100% of renewable possible. And even possible, the infrastructure or the technology needed might create excessive costs for the power systems for 100%. So this created debate and even lawsuit between these two schools. And if you are interested, there are fascinating stories about this lawsuit. And the lawsuit was dropped, but the debate has continued. That means if we learn from something from this debate or lawsuit is energy transition is difficult. And there are broad technology portfolio is needed, and there are also broad policy or political context or reality has to be considered. And those facts we will discuss in future lectures, like the uncertainties of modeling, and those will help us to have better analysis of any proposals. Our measure changing perspective or why we started to think about 100% of renewables, or even or at least more renewables. It's possible. It's this fundamental change of the renewable costs, especially during the past decade. This chart from IPCC, most recent climate assessment report, it combined or presenting in a nice way that as the adoption of renewables grow, its cost coming down. For example, solar PV from 2000 to 2020, it's achieved about from 600 to about 60 or 80 dollar per megawatt hour, more than it's about 1/10 of the cost. It's in about 20 years. And onshore wind from about 150 to now 50. Offshore wind also coming down very fast, and those from CSP and EV, the cost all coming down at the scale of 1 magnitude, especially for solar PV and EV. For those renewables, as you can see here, they all fall into the range of fossil fuel costs, which means that renewables are achieving grid parity, and they can compete in the market without subsidies in many parts of the world. And for sure, there are complexities of resources quality, and the customer might serve differently. But the message here is renewables are getting cheaper, and it can already compete in the market with fossil fuels. That's good news for the climate. And so that's a game changer. And those different drivers and different countries has already created the ambitious plan to achieve carbon neutrality by middle century, or some countries by 2060 or 2070. But it's all created the motivation to achieve carbon neutrality to address climate change. This example, the Germans example on the energy transition to really fight climate change and reduce energy imports, so enhance its energy security and stimulating technology innovation and the green economy. That's one of the drivers that if we think about future energy systems and economic systems, the new energy might be a new commanding height for economic competitiveness, and also reducing and eliminating the risks of nuclear power. We will discuss a little bit more on nuclear power, and in Germany's case, Germany want to phase out fossil and nuclear while increasing rely on renewables. It will enhance energy security and strengthen local economies and providing social justice. This is very consistent with what the hard path and the soft path has visioned, right? And this is moving towards a more soft path. So what makes Germany's case interesting as one example, it's nuclear. And this chart shows the operable nuclear power capacity over time. And for long history, from about 1980 to 2010, Germany has stable about 20 gigawatt of nuclear power capacity, and gradually phasing to about 10 gigawatt, and starting from 2020, it's up. The capacity is about 4 gigawatt, and it has planned to scheduled to shut down by end of 2022, which is end of this year, and was forced to extend it to 2024 because of the Ukraine crisis. And that's a story or an example of why nuclear lost its attractiveness in Germany, mainly due to the Fukushima nuclear crisis, and at the same time the political impact of the green groups or anti-nuclear groups that gaining grants, and then the competing need for keep the lights on or maintain the energy security that pushes a different perception of nuclear, or the role of nuclear can play in the energy transition. And you can see the dynamic factors that will change the technology options or choices of the energy transition. One message that the young generation Greta has changed the whole perception of nuclear, that think about thinks nuclear needs to be part of the solution. So this exactly shows the complexity of the energy transition discussion. And when we try to analyze or project the future perspectives, those are the factors that we have to think about, and those are also where the uncertainties are. So this is Germany. In US case, there are multiple researches to address how US can achieve net zero by mid-century. One representative study is from the Princeton Zero group that using analytic tools such as high-resolution energy system modeling to show how different technologies can achieve net zero by mid-century, and what's the pros and the cons of a different technology mix. Here are the different pathways based on the assumptions such as high electricians, this including high electricians in vehicle and buildings, which means that it need more electricity, and less high electrifications and less electrification and different technology emphasize. Some may emphasize on high biomass, some emphasize renewables, and it also discussed all renewables, though these all renewables not just about wind and solar, but also bio. So it has different energy supply and demand assumptions and technology assumptions, and it created the technology mix or generation mix from those technologies. So the implications is those would involve very different strategies on how we develop our infrastructure, for example, transmission systems, how we create incentives for different technologies, and the future will be different. So that's why it's important to think about what future we want to move towards to, and prepare or invest today as we like to. But for sure, in the end, it will impact by the markets, it will impact by the dominant technologies, if there's any, and it will impact by how the technology can adapt to local contexts and how it can compete in the market. But for policymakers, it's very important for them to create the market or incentive to move the, if we see it as a rolling ball, to start the rolling ball and get the infrastructure ready. So this offers some interesting discussions of what are the pathways and how they compare to each other, and how we think about the policy implications. What are the impacts which we assigned the assignment homework 0, that for you to think about the impact of the Inflation Reduction Act and how that can contribute to the carbon mitigation in US economy. And this study by the Rodin group and created the scenarios of the Inflation Reduction Act, the IRA, can potentially reduce emission by 30 to 40% compared to the current policy. For sure, it will rely on how the incentives, for example, tax or rebate to solar wind installation, heat pump installation, EV purchase, for example, all this will help increase the penetration of those clean technologies. At the same time, encourage the manufacturing of those products, and all this will accelerate the penetrations, and that's where the carbon mitigations come from. There are some other country case studies, such as in Denmark, how Denmark tried to increase the penetration from offshore wind and also create a more resilient energy systems to provide power and heating to local community. Is the transition from central planning to distributed generation. As you can see here in the 1990s, there are a few of large-scale power plants that provide the electricity for the whole country, which moved to 2015. Those all distributed energy systems that from primary coal-fired to local CHP plants, combined heat and power, and wind power plants and solar plants, that it's very important for those biomass CHP plants that they can absorb the excessive generation from wind and solar, and at the same time to provide electricity when there is less supply from those renewables. So this technology trend, we are not just rely on technology flexibility. It also need to, for the electricity market, change from vertical integrated monopoly to a more competitive electricity market that you can trade with the larger EU grid, or you need a system transmission system operator to serve as independent operator that provide the grid or the transmission access to all generators, and also need the price signal to really function, that to show the value of the generation at a different location and a different time. Denmark really offers a good example for how it can transit from more fossil generation to now very close to 100% of renewables, mostly offshore wind. Yet you can say Denmark might be a smaller country. Now we can talk about a big one, which is more challenging and complicated. And this chart from the economics really shows the scale and scope of for China to really move towards the announced 2060 carbon neutrality goal. In 2000, or here in 2019, China has emitted more than 13 gigatons of carbon dioxide. And that's almost the combined emission from United States, EU, Japan, and Canada. And that's the scale. And all that need to peak before 2030 and then reduced to net zero by 2060 in 30 years. While you compare to United States or EU, that's very, very common. In United States case, it's about 40 years. In EU, is more than 60 years. Japan, about 50 years. So the scale and scope of such drastic decarbonization path or decarbonization has not been seen in human history. That involve fundamental change of where China uses its energy and how it can create the market to provide the right incentive for such transition. One of the most challenging tasks in China's case is phasing out coal. China used to generate 80% of electricity from coal. Now it's about 60 and very close, move close to 50% of electricity from coal. And that's half. And that you can say that's still dominant. Yes. So the challenge is how can China phasing out its coal plants, which is already the world's largest coal fleet, and some coal plants are still very young, which was built in the 2000s, and typical coal plants can run 30 to 40 years or even longer. And this paper from Rila Cui and others create a comprehensive index to evaluate the variability of or the priority of how to phase out each power plant. Consider the technical features, the economic features, and environmental impacts. So it can rank different plants based on those indicators to create a strategy, a plant by plant strategy to phase out coal, which represent a very interesting study to develop a comprehensive strategy to phase out coal. In the real world decision, this can be way more complicated, but at least it offers some framework to how to approach such challenges. For sure, phasing out coal could yield huge benefits in terms of water saving, avoided premature deaths, and human health benefits. At the same time, phasing out coal needed to address employment impacts and welfare distributions, because those who benefit from phasing out coal, not necessarily those who lost their jobs or suffer from such transition. And for public policy, really need to create the right incentives and compensation during the transition. If you are interested in this topic, we have a paper on that, and feel free to find more information about this challenge. Now, another country, Brazil, which hydro and biomass really play a huge role in its energy mix and electricity mix. For example, more than 60% of its electricity is generated from hydro in 2019, and about 10% from biomass and 10% from wind, and the rest from fossil fuel and nuclear, which in Brazil's case is electricity already quite low carbon, only about 14% of electricity from fossil fuels. That's good. If we talk about the primary energy, it's more complicated, but still hydro is the backbone of Brazil's energy system and especially electricity mix. This create multiple scenarios or considerations. First, it's already lower carbon, and it makes it comparatively easier than other countries to achieve carbon neutrality in its power systems and the energy systems. And second, we already discussed this point that hydroelectricity is increasingly exposed to the changing climate. And it will change, the climate change will change the pattern, the intensity and availability of water resources, and that would create stress on the operation of hydro plants. So that offers another layer of complexity of how the energy systems co-evolve with the climate. Biomass is another interesting case because it creates the so-called energy, food, water nexus challenge, because you use bio to generate electricity, for example. You would need land to grow the feed biomass for power, and that compete with land for food. And since Brazil has unique and very important role in the global food market, and it might raise the cost for food supply, and that's the so-called energy, food, water nexus challenges. All those systems are linked, and those are interesting research questions related to Brazil's case in the energy transition. If you're interested, there are further readings that you can follow. One more case study is Africa. That's because African population is growing, and its population has comparatively young population, and its economy is expanding, and the energy demand in the coming decades will be largely driven by the energy need in this continent. And this paper described the even for a younger continent or young Africa, each country has very different contexts. If we think about the energy, some have high fossil reserves or energy endowment. Some has higher renewable endowments, and here shows where they are their electrification and country-specific levelized cost of electricity from solar PV, and it shows how different countries can move towards PV or still rely on fossil fuel. So this shows exactly when we think about energy transition, we have to address the geographic or socioeconomic diversity of different countries to really look into what resources it has, how the resources is aligned with its energy demand, and what technology is available what are the costs, and what are the socioeconomic factors that can potentially impact the large scale adoption of a specific technology. Those are hard questions to answer. At the same time, those questions offer new research opportunities that researchers can really contribute. So there are uncertainties. A typical one is the Ukraine crisis. A natural question is the crisis really an acceleration of the energy transition, or it offers some complexity when we think about the transition? It might both. So here, the Ukraine crisis really reshaping the energy war. As you can see here in the most recent World Energy Outlook released by IEA, International Energy Agency, that the war pushed the energy markets to high and volatile energy prices, and that hurts households and the businesses because it shifts the choices of fuels and setting back progress toward achieving universal access to energy, because disadvantaged groups and would have to accept the affordability of energy's impact. It also impacts the energy policy that short-term response have focused on security energy supply to protect consumers, and which very often may conflict with the goal to invest in clean energy and energy efficiency, because the priority to secure the supply no matter where the energy comes from. It also impacts the energy trade and has economic impact because high energy price makes manufacturing less competitive and has a big impact on the economy. Those are still unfolding how it might impact the global economy. It also has impact to carbon emissions, since Russia has cut its natural gas pipeline flows to Europe, and some countries even use more coal to generate electricity, and more coal means more emissions. CO2 emissions from global fossil fuel combustion has see a record rise in 2021, even given a strong expansion of renewables and electric vehicle. It's not enough to compensate the growth. So those factors contribute to the complexity of energy transition and carbon emission. No need to say the pandemic created disruptions of global supply chain, and also uncertainties, and they increasingly thinking of domestication of or onshore their supply chain to create economic and employment and other local benefits. All this will have an impact on the economy of the global clean energy transition. So to summarize, we discussed the diverse factors that drive energy transition, and there are discussions about common and differentiated solutions to energy given the context of each country's, and the debate of 100% of renewables versus more customized solutions or broad portfolio of technology solutions of the energy and carbon neutrality challenges. In all, we have to think about how to levelize or leverage the advantages in the context of local availability, and try to align the energy technology with the spatial and the temporal needs of the local customer or local use. At the same time, address the uncertainties along geopolitics, wars, pandemic, and other uncertainties. Here, I listed some of the papers we discussed in this lecture, and if you are interested, you can just go to find, and they offer very good background and debate on the topics that we covered today. That's all for today. Thank you.